Okay, so the idea here was to focus on urban environments, because I cannot cover everything about microbes everywhere on the planet, and sort of identify some vulnerabilities of our metropoles with regard to our interface with microbes. And we've already heard a lot about microbes in the first and the second talk in this session. The idea is to sort of project ourselves possibly in the future and consider how climate change, of course global warming, part of this climate change, but also human behaviors, everything that is part of this Anthropocene concept, I mean, changes in diet, medication, and so on and so forth. How is this going to affect, in a very specific environment, which is the urban environment, our health? At the end of the day, that is the question here. So I don't want to go back too much onto some numbers and figures, and you've heard already from Chris. It's obvious that, at least I'm not too corporatist about it, believe me, but still, I think that in the narrative of modern ecology, I mean, microbes are a bit forgotten in a way, and I'm glad that ocean microbiome has been put up on the stage now. So, I mean, in a way, of course, the macroscopic life world is huge. I mean, it's 85% of the planet biomass, and it's essentially dominated by plants. Like I've put that in gigatons, which I think is interesting. There are 470 gigatons of plants on the planet, and only 2 gigatons of human and animal flesh, I would say. On the other hand, microbes, of course, are behind it. It's only 16% of the biomass, but it's 95% in terms of biodiversity. So, I mean, and we all know, of course, that microbes are important in terms of their role in the big cycles of life on the planet. This has already been mentioned. Microbes are very important as symbiotic microorganisms to the plants, for instance. There will be no good agriculture without the microbes in the rhizosphere. They are good at depolluting soil and ocean. They are also symbiotic to animals and humans, of course, and this is all about the issue of the microbiome. We used to see the human microbiome as a sort of sensor, integrator and effector of the environment. And it's, in a way, a possibility for us as humans or animals in general, physiology, to be able to possibly react more rapidly to some environmental changes, because the microbes themselves have this capacity to evolve faster by their capacity to mutate, or their capacity to undergo some transfer, some lateral transfer of genes from other microorganisms. So all this is kind of a very fascinating symbiosis, and I hope we will have a chance to come back to this. Not forgetting to say that, again, we are living in the same environment. We are sharing the same environment, humans, animals, microbes, plants. And this is all, of course, about this new, or not so new concept of one world, one health, which sort of considers under different angle these very fascinating aspects of interactions. So, I mean, if we now look at the urban situation, it's clear that the city, the big metropoles, they sort of aggregate all the risk factors with regard to alteration of microbial ecosystems and their impact on human health. The issue, of course, is a growing issue, because as the world population increases, 8 billion last October, the urbanization rate also increases, and increases quite fast. It's largely now over 50%, and it's anticipated to be about 75% probably by 2050. And this is really making the urban environment as a per se concept that we need to try to explore in this context. So what are the vulnerabilities of the big cities, knowing that at the moment on the planet there are 20 metropoles that have more than 15 million inhabitants, and half of them are in middle to low income countries, which means that the threat, of course, is even higher for these metropoles. So, of course, there is an issue of public healthness, an issue of clean water, an issue of safe food. that is very important to be considered, and that's going to be a target possibly for microbes to alter under this climate change and other changes in behavior. Cities, of course, are really places for possibly epidemic development, and this has been addressed by Professor Haynes. There's many reasons for this. Of course, the density of the population, especially for air-transmitted microorganisms, public transportations, gathering, cultural sports gathering. We've seen that during the COVID-19 period. There is also the issue of poverty, which is a major driver for changes in ecosystems, microbial ecosystems, and risk for infection and the complications of these infections. I mean, you can list all these vulnerabilities of the cities, not even speaking about the fact that these big metropoles are often home for big air transportation hubs, and we know the role that these places have in the transmission of epidemics to the whole planet. One thing that has been addressed already is what we call the entomological risk, which is the development of vectors in urban situation, in urban context. And this is clearly a situation that we are facing at the moment in France with Aedes albopictus, which in a matter of 20 years has basically from south to north colonized the entire country, taking advantage of its better adaptation to our conditions. Eggs are very robust, but also transportation. I mean, clearly railroads and routes have been important in this colonization. And we are starting to see now secondary or tertiary cases of dengue, for instance, in the south of France, in the area of Nîmes, for instance, saying that maybe in the near future we're going to have dengue becoming epidemic and possibly endemic again on the long term, as it was at the beginning of the 20th century. So this is really a threat, and this shows in a way that we haven't probably addressed enough this risk, like by education of the population. I don't have time to get into this. And our cities are not really ready to cope with this situation, with these new vectorial cycles. There are some WHO projections saying that in the field of public health, I mean, there will be probably by 5 to 10 years an increase of about 20% of food and waterborne infections. Okay, so I think there is one issue that is very important when you give this sort of global pictures. Is there a way to sort of acquire, as it's been done with Tara Ocean, a sort of global picture of the urban microbiome? It's a bit of a provocative term, but it's something that is currently developed by the help of big data, new generation sequencing, and bioinformatics, of course, gives you fantastic tools to study some urban ecosystems. Question is, very often these ecosystems present a very low biomass of microorganisms, like air, for instance, or like handles in the subway. I mean, these are sites where you would like to know exactly what's going on at one particular time. But this opened the way to contaminations of these samples. And so this is a very subtle and delicate approach that has to be conducted with a lot of controls. But still, this is on the way. It has been developed, for instance, in Singapore, in housing systems to detect new emerging microbes in the environment of these places. And like Aspergillus or other of these microorganisms are now detecting using this kind of approach. That's the work of Stefan Schuster, for instance. But there are some different angles under which these new technologies are now used to identify or define some of these urban microbiome aspects. For instance, there has been a paper couple of years ago dealing with 60 different cities on the planet. And doing this approach in some hotspots, I was talking about, handles in the subway. I mean, these kind of places where lots of people meet on an everyday basis, But other hotspots, of course, exist that you can imagine. And each of these cities has some sort of different signatures that are marked of their identity in a way, depending upon many factors that you can imagine. You can also follow there are lots of new species that are detected, a lot of new viruses that are circulating for which we had no idea before. Again, it's a bit the world of silence that is revealed at this scale by these approaches. And this is, of course, the beginning of a proactive way of surveillance of these urban ecosystems in the future. Of course, there are approaches that look at the impact of high temperature. This was done in China, for instance, showing before and after a canicule that the air composition in terms of microbes had changed with a switch towards firmicutes, which are gram-positive anaerobic microorganisms, very much sporulating microorganisms. How much of this may have impact on health? It's not known yet, but it's on the way, and we have to continue these studies. Nairobi, Kenya, they've done studies on hotspots where humans, domestic animals, and wild birds meet in some areas of the city, 90 or 99 places, different hotspots in the cities. And they have shown very well that there were a permanent exchange of microorganisms between these three different populations, and that these exchanges, especially from wild birds, were kind of structuring these microbial populations. So this is very important, for instance, to anticipate on the occurrence and development of a possible zoonotic infection. And these tools are increasingly, of course, used. I would also like to mention some new approaches, this new few years ago now, but it's been crystallized during the COVID-19 period. Aubépine in France, but in different other countries in Europe and in other places in the world, which look at the composition of the wastewater before the purification stations. And this is a way giving you an angle on this urban microbiome, because all this fecal material that we are basically, I'm sorry, before the lunch, but defecating in these wastewater pipes is basically a reflection of us, of our microbes, virus, bacteria, but also now of our drugs, the medication that we use. It allows us to look at the antibiotic consumption, for instance, on psychotropes consumptions, hormone consumption. And this is much more sensitive in a way than just looking at the pharmacist registers and trying to see how much of these medications have been sold. So there is a kind of revolution here, which I think is important to measure what this could be. So to sort of cover one of these vulnerability, it's obviously water. And I will go fast on this, but this is a very important issue. It's clear that we need clear water, but the increase in the world population, the restriction on water availability, the increase and legitimate demand for good drinking water, for instance, as well as the changes in climatic conditions, is going to be like an explosive cocktail with regard to availability of safe and high quality water in big cities, in big metropoles. In our metropoles, in industrialized country, the purification of water is based on good technologies, sedimentation, the microbe filtering, the issue also of reverse osmosis. All this is carried out, and at the end of this pipeline, after the purification, usually the microbial is several order of magnitudes and below and sometimes zero colony forming units. So the water is bacteriologically absolutely pure. But this is unfortunately not shared by more than half of the world populations in these metropoles, where the standards of quality are not the same. But it's not just to clean up this waste water, it's also to ensure that the distribution is not again contaminating. And it's clear that there are bacterial ecosystems in the water distribution system, this huge network of pipes. Flavobacteria, for instance, is a kind of proteobacteria that is dominant in this system. And it's clear that even if these microbes are not pathogenic, they might be pathogenic for immunocompromised people. So this is a very sensitive marker that has to be surveyed. And clearly, one big issue that emerged from all this is biofilms. Biofilms is a very important element which shows that microbes in any ecosystem live in communities. It might be single communities or it might be multi-species communities. And this is very essential because it's a way for the bacteria to survive, basically, in the environment, in many, many places. There are pioneers, microbes, that start to adhere to a surface, whatever it is, a biotic or an abiotic surface. And then they start growing and they develop regulatory mechanisms which allow them both to reduce their metabolic activity and survive, as well as to produce massive amounts of polysaccharides, of proteins, releasing DNA, and all this forms this kind of protective layer that allows them to survive in the environment to whatever aggression they could undergo. It can be antibiotics, for instance. They are resistant to antibiotic in these systems, but it can be also chlorination, for instance, that is used in the cleaning of water. So it is clear that this is going to be an issue. So let's look at two examples. One, which is how the wastewater is conducted to the purification station. It goes through these big, pipes that are made of concrete, and it's clear that microorganisms are not good for concrete. They tend to colonize the surface and the matrix. And what they do is, because they are essentially anaerobic microbes, they acidify. And we heard acidification about ocean. It's not good for ocean, it's not good for pipes. What it does is to induce cracking and the crumbling of the concrete matrix, and this leads to a destruction. And it's clear that these microbial population, these biofilms in experimental models, they increase in size, they increase in microbial density, they change their microbial density according to increases in temperature. So this is going to be one of the vulnerabilities, and one of the major microorganism family is Thiobacillus. They are anaerobic. They produce by fermentation. There are nutrients, of course, in these wastewaters. They produce acetate, they produce lactate, they produce butyrate. These are organic acid, but they also produce anorganic acid. These microbes are involved in the sulfur cycle, so they basically oxidize the sulfur and they reduce the sulfate. And all this leads to production of acids like sulfuric acid, which is very aggressive for concrete. In fact, the major protective element in terms of chemistry of concrete is the pH. It's very high pH, 11. And within hours of development of these biofilms, you might see that the pH goes down towards sometimes pH 3, which is pretty acidic and destructive again for the concrete matrix. So all this is an issue that has to be taken into account. Of course, we see similar situations in the distribution system, where these flavobacteria also have this capacity to decrease the pH. And this, interestingly, is of course altering the quality of water, because the microbial composition increases. It also increases in diversity. There are some ecological succession that are induced by these chemical elements, and basically when you look, especially using this big data analysis, you see that it's not just these flavobacteria, it's a lot of new microorganisms that were present in the sample at very low density, which are now developing, and this also includes, the fungi and molds and so on and so forth. So there is a whole ecology of this that has to be studied because it is essential if we wish, for instance, to keep water quality and to keep the distribution system from corrosion. One big issue again is biofilm. The way we clean up this distribution system, we would say, is very archaic. What we do is flushing and also, chlorination. But these biofilms make microbes resistant to chlorination. So there is really a need for good science here, for innovation in terms of treating these elements. I would just like to finish up on 2 slides and make it very short. I've been talking about the climate changes and global warming in terms, for instance, of facilitating biofilm developments and corrosion of water collection or distribution systems. But we are also living in a world where we are ourselves, by our behavior, altering microbial composition of these ecosystems. And this is the crisis of antibiotic resistance. The situation created by Anthropocene is that we are exaggerating in using antibiotics in the medical and veterinary environment, of course, but a lot has been done here to educate the doctors. But still, more than 50% of the antibiotics that are used in the world are not used for medical or veterinary purpose. They are using for cattle breeding for 2 reasons. One, for sort of prevention of infections, and the other one is because they are good growth factors. And this goes also for fisheries, for instance, where tons of antibiotics are released in waters every year in many places of the world. Fortunately, it's prohibited in the European Union. But basically, we think that about 300,000 tons of antibiotics are released intact on the planet in many, many different places, but urban sites, of course, are very essential as providers of these antibiotics, as well as the intensive breeding facilities in some places of the world. So this causes the antibiotic resistance crisis because this low concentration of antibiotics that we can even find in the river now, they maintain selective pressure on what's called the resistome of these microorganisms in the environment that facilitates the survival of those that are resistant to antibiotics, especially to trimethoprim and to fluoroquinolones, for instance, which are not necessarily well degraded because they are chemical elements. They are not produced by plants or by microorganisms themselves. And so my last point, Jean-Marie, I apologize, is that, maybe this antibiotic resistance crisis, which is clearly linked to human behavior, has hidden another crisis, which is the crisis of microbial biodiversity. And it seems that this crisis of microbial diversity in association with humans is something that now needs to be really put on the table for the reason that I said, because our microbiome, which is sensitive to these antibiotics and other stressors that you can think of in the environment that the Anthropocene has created, our microbiome are suffering from this, and it's sort of developing what we now call a dysbiosis, a change in microbial composition, a change in microbial diversity, which tends to reduce. This leaves space for what we call pathobionts, which play a role. And we can see a lot of now correlation, but also experimental proof of demonstration that this biotic situation that is created by the Anthropocene is probably the cause of these famous now epidemic, non-communicable postmodern diseases like allergy, atopy, obesity, diabetes, cancer, colon cancer, for instance, not necessarily the essential cause, but at least factors that facilitate the development of this pathological status. So we really need to take all these elements into account because, again, this all changes that is prepared by the aggravation of human behaviors with regard to bad eating habits, and all this is concentrated in cities, for instance. Of course, pollution and other elements are impacting a lot on this microbiome. And this is really a new science that is emerging, which is important to consider. So I will stop here. Sorry about some minutes that I took that I didn't deserve. Thank you very much.